Recording is on.
Hello everyone, welcome to today's session of this webinar series organized by the Young International Committee of Predictive Modeling in Foods. Our society, yICPMF, is a global initiative of early career scientists working to promote education, collaboration and knowledge sharing in the field of predictive microbiology and food modeling. This free open access webinar series is part of our mission to build a strong international community by connecting students, researchers and professionals with experts in the field. We are really happy that you're joining today, whether you are here live or watching the recording later on. Let's first go over some housekeeping rules. So today's session is being recorded and both video presentation slides will be shared with you afterwards. Please also keep your microphone muted during this talk. You can type your questions anytime in the Q&A document or in the chat box. We'll collect them and present them to the speaker during the session or in the Q&A at the end. Also, make sure that you stay with us until the end of the lecture and webinar. At the end, we will also ask you to fill out an attendance form, which is required in order to receive your certificate. We will also be taking a group picture for our LinkedIn post after the Q&A, so we kindly invite you to turn on your cameras at the time if you're comfortable, of course. Feel free to engage with our network via our Slack community and follow us on LinkedIn for updates on upcoming webinars. If you have any technical issues, please message one of the hosts directly into the chat. And now it's our pleasure to welcome Professor Skandamis as our speaker of today. Professor Skandamis is a professor of food microbiology at the Agricultural University of Athens, and in addition he serves as vice chair of the Biohazard panel of the European Food Safety Authority EFSA. He has authored 297 research papers in Journal of SCI, 32 book chapters, and edited one book himself. His expertise lies in the control of pathogenic microorganisms in food and the application of predictive microbiology and quantitative microbial risk assessment, or QMRA, promoting systems and risk-based thinking. Our professor is also a founder of Growth Predictor. This is a web-based predictive modeling and QMRA software, and he is also editor-in-chief of Journal of Food Protection and received the Maurice Weber Food Safety Award in 2021 and also the International Leadership Award in 2023. He is also a member of the ISO Working Group 23691 called Microbiology of the Food Chain, Determination and Use of Cardinal Values. Yesterday, the professor gave the first session of this webinar, which was focused on fitting primary and secondary models, as well as running deterministic and stochastic growth models using constant or dynamic conditions with the software he will talk about. Today's webinar will be fully dedicated to the modular QMRA's module of his tool. Professor, please, the floor is yours.
Thank you very much, Bram, for this nice introduction. I welcome you all again for our second day of the webinar series. I'm very pleased to give this talk that, as Bram mentioned, is focused on QMRA, Quantitative Microbial Risk Assessment, a module that is also served by the Growth Predictor, the tool that you see on the screen, and the link I shared yesterday. So the concept is that I will provide, as I did last night, some background context information about QMRA, explain some fundamental principles which are used or serve as a basis also for the QMRA feature of the growth predictor. So let's start first of all with, as we did with predictive microbiology, the fundamental definition of risk. According to Codex Alimentarius, risk is defined as a function of the probability of an adverse health effect and the severity of that effect consequential to a hazard in food. Apparently, we are focusing here on the microbial hazards. So we're talking about pathogens that can cause infections or intoxications. So risk eventually is a product of probability times severity, or else called impact. And as you may see, if we have low scores for probability and severity, then we have a low risk. And the counterpart of this product is the situations where the probability and the severity receive a high score quantitatively, that leads to very high risk. All the intermediate situations, as shown here in the kind of very fundamental heat map, correspond to intermediate values where either probability is high and severity is low, or severity is high but probability is low. And this, of course, graph can be interpreted in multiple different ways, depending also on the type of the microbial hazard or the chemical hazard. It can be used both ways, but focusing on microbial hazard, depending on whether we have intoxication, whether we have infection, and of course, this impacts certainly the severity of the risk associated with the hazard. Risk assessment can be done in, I would say, more or less three different ways. Could be fully narrative, which is something that we can do very rarely when we have totally lack of data. So it can be also called a qualitative approach. But it could rely only on evidence from the literature without real data to populate our assumptions, our interconnection between the different parts of the risk assessment components, etc. It could be also done qualitative, narratively, but in a more, let's say, understandable, graphically speaking or diagrammically speaking way, such as the decision tree that you see here, where the answering a series of questions with a binary way, yes or no, then you can end up with a risk assessment output in terms of a nominal scale or an ordinal scale from low, medium till very high levels of risk. And as you can see here, the questions are relevant to the behavior of the microorganism, such as if the microbial treatment, if there is a microbiocidal treatment without recontamination, if there is such a treatment, then the risk is directly low. If there is no such microbiocidal treatment, then we have to ask ourselves, does the product support growth? If it doesn't support growth, although there is no microbiocidal treatment, then again the risk is low. But if there is a growth supporting product, then we have to consider whether toxin production is possible. If it's not, then again it's low. But if it's not, if it is possible, then we have to think whether toxin is heat resistant. And if it's no, then because it is a toxin, we have to consider whether we have an extra step of cooking. And if we don't have an extra step, then we don't have a low risk, but we have a medium situation due to the presence of a heat toxin, a non heat-resistant toxin, but still is a toxin. And if we have, of course, a heat-resistant toxin that is not cannot be even eliminated by any consumption, any cooking before consumption, then apparently the medium risk becomes really high. So this is an example of a narrative, I would say, qualitative approach, but based on a decision tree. Of course, we may have semi-quantitative approaches in the same line, where we end up with an ordinal definition of risk from 0, for example, to 10, but still relying on answering questions, probably providing a score instead of a yes or no to an answer. And this is definitely a way to go with discrete instead of continuous answers. However, I think the optimal situation, which requires, though, the highest number of resources, and that's why we need some tools, especially for the non-expert users, is when we want to apply a full quantitative microbial risk assessment, where the definition of risk and the input variables and all the interconnection between the input variables are represented by continuous distributions or by causal relationships like predictive models that we described yesterday, that use continuous inputs and provide outputs in a continuous form. So in this case, if we have a full QM array, then the risk metrics are one of these two fundamental categories. Either the adverse outcome, like illness, and its likelihood per serving. These measures are, in fact, the risk that individual consumers face when they eat a serving of a food. This means practically that this is a function of the dose that has been consumed, which is also a function of the prevalence of the pathogen. So, in other words, the likelihood that the product is contaminated and that the consumers buy a product that is contaminated, the serving size, and the amount of the hazard that has been achieved in the food or is present in the food by the time of consumption. But still, this is associated with the individual risk that is associated with the risk for each individual serving. If we know how many servings we have for a given amount of time, like usually we use the annual basis, then the adverse outcome per annum, standardized or not for a population size, for example, as we use for incidence rates per 100,000 population per year, then by multiplying the likelihood per serving with the amounts of servings, we measure the risk faced by a certain population. Could be a country, could be a continent like Europe, or could be even a global assessment. Apart from the risk metrics, the classical risk metrics of risk per serving or total number of cases, predicted cases, or expected cases per annum per population, we can also measure the risks in a different way, the measures of public health burden. So there are metrics for characterizing the severity of the public health and compare their overall health to or economic impact. This way we can do what we saw before in the previous slide, also the relative risk associated with either multiple hazards in a given food, multiple foods for a given hazard, or a combination of the two. And the reason that we want to have this type of metrics about severity is to be able to, as we call, normalize the different hazards based on their severity. Because, for instance, the impact of gastroenteritis is not comparable to that of a systemic infection that requires hospitalization or may cause permanent disability or death. This way, we can compare the risk outputs of diseases that are communicable versus diseases that are not even foodborne, like, for example, cancer or maybe a heart attack or coronary disease, or even deaths or injury that comes from reasons, causes like car accidents or any other type of health burden. So this way we can have a general assessment of how important, what is the burden of different reasons for a person to become ill or to become disabled or even to die. Usually the most prevalent severity metrics, risk metrics, is the so-called DALIS, CALIS, or HALIS, which measure the disability, the years lost due to disability or premature death, the quality, which is also introduces the financial metrics, and the health adjusted life years, which introduces the hospitalization, the reduction of the loss of years due to in comparison to life expectancy, which is about 70 years old now. It used to be much lower at the early 20th century. And this can help us, as we say, to estimate the burden of disease for the relative impact of specific illnesses and conditions on communities, also introducing the economic feature. I chose, as we do with EU Fora training seminars for EFSA, I chose a typical example where the DALIS, which is a very commonly used metric, to show how can be calculated for a person that got a foodborne illness at the age of 10 and dies at the age of 50 when the life expectancy is considered to be 80 years old. This means that if the person died at 50 years old, it means he died 30 years before the average life expectancy. So this person lost 30 years of life in comparison to the expected lifespan. On the other hand, since the person got ill at the age of 10, and then he lived another 40 years with 20% of disability, it means that it lived for these 40 years as being equivalently 10 years at full disability. This means that the full disability of 40 years with 20% disability is equal to 10 years of full 100% disability. So 10 years due to disability and 30 years due to premature death, this gives a total number of 40 dies. And you can make relevant calculations for other type of hazards. And let's go now to the risk assessment infograph. So we talked about the risk as a definition. We talked about the severity metrics. So we talked about the risk metrics and the severity metrics. Here, for the needs of this particular session, we will focus mostly on the risk metrics, which is the risk per serving times the number of servings equal to the expected number of illnesses per population per year. So we will deal with the calculation of these two measures here, both at the theoretical level first and then at the practical level through the growth predictor. The risk is, as we said at the beginning, is a function of the dose and the severity. So let's talk about first about the dose. The dose is actually something that we calculate through risk assessment by the component of risk assessment called exposure assessment. And the dose is a function of the chain, first of all, of the possibility that a hazard is introduced into the food chain. Here is a typical example, simplified, I would say, but not a lot far from reality, of the whole food supply chain from primary production till the consumption. You may add as many intermediate steps as you consider appropriate, but let's have a generic approach that is understandable and transferable to most real-life situations. So first of all, as a starting point, we identify the hazard. So here we have all the components of the so-called risk assessment. First, we identify the hazard of concern, and then we identify the point of entry. This is also part of the prevalence, because not all foods are contaminated, so the percentage of food that are contaminated represent the prevalence of the hazard. Then, by the time the hazard is introduced into the food chain, depending on the intrinsic conditions of the food and the processes, the outside conditions we impose by the processing and the distribution of the food till the consumption, including the cooking by the consumers, are responsible for increases or decrease or re-increase of the surviving population of the hazard. At the very end, including also, if applicable, a cooking stage by the consumers, this defines the amount of hazard that is ingested by the consumer. This amount of hazard ingested by the consumer, so this completes the exposure assessment part here, it is fed into the so-called dose response models. The dose response models represent the hazard characterization component of the risk assessment. The hazard characterization, in other words, a dose response, translates the ingested dose into a probability of illness. And this automatically gives us the probability of illness per contaminated product. If we take into account the prevalence, which is the likelihood or the percentage of products that may contain the hazard, then we can convert the probability per contaminated product, if it is multiplied by the prevalence, into the probability of illness per serving. Of course, somebody may argue, and this is actually true, that the amount of serving, whether you eat 25 grams versus eating half a kilo or even a kilogram, is also a determinant of the probability either of the contaminated serving of illness, either from a contaminated service or from a serving in general, taking into account also the prevalence. And once we have calculated the probability of illness per serving, multiplying them by the number of annual servings, automatically we are estimating the number of illnesses in the population per year. Before I move further, I would like to link this graph with what Thank you. So before continuing, I would like to link this graph with what we discussed in our yesterday session. So the estimation of the exposure or of the dose to be ingested by the consumer, including the impact of cooking by the consumer, can be calculated in silico through computer-aided simulations with predictive microbiology tools. So as you can see, we can use cumulatively, serially, okay, predictive models that predict the growth or the inactivation, and again, the growth of the hazards throughout the food supply chain, both under constant, average, or stochastic conditions, and also under dynamic conditions. And then we will come back later on with the impact of the variability and uncertainty, which provides statistical power and realistic estimates of the risk. This is a typical example. I chose to include that here from an opinion of EFSA biohazard panel in 2017, the one about listeriosis in EU. This is the conceptual risk assessment model that we used in this opinion. It's a far more realistic perspective. So you see that we have the following food supply chain components: primary production, processing and packaging, retail, and preparation at the domestic environment. The key issues here is the prevalence, the concentration, and the sample size. In letters here, you see all the factors that contribute to the formulation, the value of the prevalence, the concentration, and the sample size. So depending on the food supply chain, we may have, for example, factors that affect the prevalence, the introduction of the hazard, in particularly Listeria monocytogenes, and the concentration, first of all, at the entry point of the food supply chain. And P stands for prevalence, C stands for concentration, and U stands from sampling size. If we proceed further with the processing and packaging, then we have to consider the raw materials, the processing conditions, the post-lethality treatments, the competing flora of the raw materials mixed together to formulate a food. And then if we move at retail, we have to consider the likelihood of growth depending on time, temperature, the food formulation, the packaging atmosphere, and occasionally, such as when we slice the big bricks of ham into slices, we may have an additional cross-contamination events, which reflect the so-called hygiene failures. And the same can be done at the domestic environment, which is usually a smaller period of storage compared to maintenance of the product at retail or in between retail processing and domestic storage, where here we may also have time and temperature affecting growth. We may also have additional cross-contamination, but I would say that we have also the possibility of having a cooking step. Here you don't see a cooking step for the apparent reason that this risk assessment refers to ready-to-eat products that are expected to receive no further cooking before consumption. Okay, then again, as the infogram, so the serving frequency, the serving size, and all the previous calculations of the changes in prevalence and concentration are used to estimate the dose. And through a dose-response relationship, we can estimate the probability and severity of illness and then convert that to the expected number of cases per year. So this is a practical example. You can refer to this Listeria monocytogenes opinion of biohazard panel in EFSA of 2017, where you can search for more details around the process. In a more simplified way of a QMRA model, you can see here, practically to me, both this and the previous infograph reflect the same thing. The one in a horizontal outline and the other one in more vertical. So here is a more simplified case because we have selected the storage temperature and storage time as the influential factors for growth. And once we have these conditions, we need a growth model to estimate the growth during storage. And then we may apply a heat inactivation model to simulate the impact of cooking practices on the final concentration at the time of consumption. And then, depending on the serving size, you may estimate the ingested dose. And through a dose response, you estimate the probability of illness per contaminated serving. And as I mentioned, if you know the prevalence, you can correct this probability of illness per contaminated service to the probability of illness per serving. And if you know the total number of servings, multiplying this gray number here in the gray box by the total number of servings per annum, you convert this probability into total number of illnesses per annum. And also to link this with the severity metrics, if you know the amounts of DALYs per case, then you can estimate the total DALYs per annum. So it's like a serial process when you cumulatively estimate the growth and the inactivation of the organism, and through that, involving or not a cooking step before consumption, you are estimating the dose, and the dose is used as an input into a dose response model. I must tell you here that the selection of a dose response model is phenomenically very simple process, but is very critical for the uncertainty of the estimated risk. So we have to pay a lot of attention on the availability of these dose response models and have a proper and mindful selection of the proper dose response model. Of course, in the scheme of the literature, we have made a lot of progress in the availability of dose response, but not for all hazards. So you have to consult available guidances, available review articles, or available reference documents for the proper dose response model. And still, we have quite many uncertainties associated with the dose response because, as I addressed yesterday, with strain to strain variation in growth limits, we have variabilities in the capacity of the strains to cause illness, as well as in the sensitivity of different individuals as consumers to the exposure against the hazard. So here we're introducing the variability versus uncertainty. I consider this a very critical set of definitions because many people like to think deterministically. But remember, risk assessment is a probabilistic exercise. And when we talk about probabilistic exercise, and since we want to focus on quantitative continuous microbial risk assessment, we have somehow to be able to quantify or to consider at minimum the variability and the uncertainty. Otherwise, we can always approach the same risk assessment from a narrative perspective, giving our textual assessment or textual estimates about whether risk is low, medium, or high. Of course, this can be used for decision making, but it would be much better if we can provide our assessments directly in quantitative terms, like 1 every million, 1 every 10,000, and so on. So what is variability and uncertainty in order to be accommodated and accounted for in the risk assessment exercise? Variability is the natural variation of a measurable with question mark property. For example, growth limits, temperature, single cell lactime, product characteristics like pH, water activity, preservative, CO2 atmosphere in the headspace. Remember the examples we went through in the yesterday's seminar. Even cooking temperature or cooking time between consumers. Even when we are asked by a waiter in a restaurant, how would you like your steak to be cooked? Providing an answer, well done, medium, medium rare, we are actually replying to a hidden question about cooking preferences. And cooking preferences cannot be introduced as cooking preferences into risk assessment because this is a descriptive variable, but they can be introduced as a combination of time and temperature of cooking in order to satisfy the consumer preferences. And this variability is due to a variety of reasons. Usually we refer to terms like sources of variability. For example, it could be strain to strain differences. Genetic noise, a very familiar expression of my friend Kostas Koutsoumani's, a genetic noise that is responsible for the phenotypic noise. Handling practices, the handling practices by different consumers. Food chain conditions, to what extent the different foods are stored under different temperatures at retail, accidentally, because we don't want to abuse the products in temperature, but accidentally, if the products of the same batch follow a different supply channel, then they are accidentally, inevitably exposed to different time temperature conditions. What we need to remember about variability is that it cannot be reduced by more measurements. It can simply be described in more details. So the more we measure, the more we reveal, we unmask the hidden variability. But certainly we cannot reduce the variability in nature. We cannot interfere with that. On the contrary, uncertainty is usually called the substantial lack of knowledge about a parameter due to insufficient methodology or lack of studies or data. Now, I want to draw your attention what I mean by parameter. A parameter could be a distribution parameter or a model parameter. When we refer to a model parameter, for example, in the Barani model, we have the H0, we have the mu max. In other models, we may have the lag time, or we may have again the mu max, etc. Or in secondary models, we have, for example, the minimum temperature allowing growth. So a model parameter is a parameter of a mathematical expression. On the other hand, there is another mathematical expression which describes a probability distribution. For example, a normal probability distribution is described by the average and the standard deviation. The question associated with uncertainty is whether we are sure about the average and the standard deviation of a normal distribution. Another distribution that is commonly used in risk assessment is beta distribution, usually for prevalence, or even more commonly and understandably is the PERT distribution, which has a minimum and most frequently occurring, the mode of the distribution, or a maximum value. The question is, okay, we can always give some hypothetical measures and values about these parameters. How sure we are? Do they follow another distribution that describes our uncertainty about the true value of each of these parameters that describe a variability? So imagine the combo situation, the hybrid situation. A variability distribution, such as a normal distribution with an average and standard deviation that describes the variability of temperature. And then imagine a hidden next distribution that is the uncertainty distribution of the average or the standard deviation of the variability distribution. This is a two-dimensional risk assessment. Of course, things get more and more complicated, and we cannot expect that a single tool can handle everything, but it's good that besides selecting a tool to do our job, it's nice that we know the general principles in order to make the wise and proper selections of how to approach a problem to get reliable risk estimates. Now, how do we do a quantitative risk assessment? I would like to call this example as the example with the car, the example of the car and the driver. So the car moves because of the engine, and the engine is a technological miracle. There are a lot of complex connections and mechanisms that are responsible for making the car to move. But the driver, as the end user, does not need to be a mechanic to drive a car. He needs or she needs to pick up the steering wheel, the gear, and the pedals, okay? And then be able, by a proper combination, to make the car moving. So the core of risk assessment is the Monte Carlo analysis. There could be other ways of performing the same work, but let's stay on the most commonly used, the Monte Carlo analysis that can be used to sample from a variety of distributions associated with variability and or uncertainty consecutively in order to estimate the final outcome. So this is a typical example where we have distribution A that describes the variability of temperature, for instance. Then we want to add the probability distribution B, which describes the variability of another parameter. And from the sum of these two, we need to subtract a probability distribution C. That could be, for example, the log reduction due to cooking. This calculation, instead of adding a point estimate, a deterministic value for A, B, and C, we want to add actually all the possible combinations sampled from the distributions A, B, and C in such a way, A plus B minus C, to deliver the final distribution. That could be, for instance, the distribution of the dose that is ingested, which, because all the previous, or at least one of the previous elements was introduced stochastically as probability distribution, also the final output is determined stochastically. And I want to draw your attention on the fact that even if A and B were a single value, deterministic value, the fact that to calculate the D distribution, the C variable is introduced stochastically as a probability distribution, even if A and B were single values, the D output would still be a distribution, because the A and B constant values should be combined by multiple samplings from the distribution C. So you understand the impact, okay, of introducing the inputs of risk assessment as probability distributions in a stochastic way. And this is what is done in practice. I have made a kind of manual small simulation. We have the concentration of the microorganism. We have the log increase because of time and temperature during storage. We have the log reduction due to cooking, and we have the concentration as an output of the dose at the cooked product. Then multiplying this by the serving size, we get the final dose that is ingested, taking into consideration the initial level, the storage, the log increase during storage, the reduction due to cooking, and the serving size. As you see here, the science indicates the causal relationship between the different distributions. So what we do with Monte Carlo simulation is we perform multiple samplings from every single distribution for every and each of these distributions. And these samplings are annotated here as the black bar. So I move back and forward now, together with the speed of the internet, in order to see what is a minimal simulation of Monte Carlo. So by sampling different values from these distributions and applying the same calculation scheme, adding storage to concentration and subtracting the levels of reductions due to cooking, multiplying by the amount of serving, automatically gives different dose as an output of our risk assessment. Now, the Monte Carlo simulation is intended to sample across the whole range of values described by each probability distribution. This is informed, this is transferred as a command to the risk assessment exercise by increasing the number of iterations. Apparently, you can do only 2 iterations. Nobody will say that it is illegal. It is not illegal, but it is not representative, because you are sampling from a big distribution, a wide distribution, only 2 times. You can do it for 10 times. Nobody will say it's wrong, but it's not realistic. So usually we want to increase the number of iterations, depending also on the available resources, computational resources of the system. And this is another infograph which summarizes what we said before, okay? It's exactly the same infogram as the simpler one I showed you before. We have the food supply chain as different modules. Each module represents a different compartment of the food supply chain. And we have the point of entry of the hazard, and then we have the increase, reduction, re-increase, recontamination of the food, plus the impact of cooking. I consider this is a more representative risk assessment infograph. So you see here that from primary production to processing, you may have an increase. The processing may introduce or not a reduction, but it may also introduce a recontamination post-processing. This is the case of Listeria monocytogenes, for instance, in ready-to-eat foods. And then throughout the consecutive distribution or retail stages, or even domestic environments, you may have a cumulative increase of the hazard depending on the time temperature conditions. And then when we reach at the point of consumption, the consumers may apply or not a cooking. So the cooking is responsible for this reduction in green. So now think that each of these factors, including the product characteristics, may have a variability. So you may have variability in temperature that can be described by probability distribution. You may have variability in time in the different stages. You may have variability also in the processing conditions. And you may have also variability in the intrinsic properties of the foods, as I showed you in our yesterday webinar. The most important is that this variability in any of these sources introduces variability also in the growth prediction or in the inactivation prediction. Again, as I showed you yesterday, so don't forget to always link what we said about predictive modeling as a tool, as a principle, as a foundation for estimating the risk. So this variability in temperature, time, product characteristics, processing condition introduces variability in this cumulative assessment of the dose. And if you introduce variability also in the cooking preferences, so the eventual dose that is ingested may follow a variability distribution that without cooking points at very high levels, but with cooking may point also at very low levels. That's why we have two distributions here. We have a narrower distribution where cooking is not applied. So the variability in this dose is reflecting the variability between these dotted lines, the variability along the food supply chain till the consumption. This is practically the variability for the ready-to-eat foods contaminated with listeria. But if we talk about, for example, Salmonella, E. coli, which are usually the problem in many foods of animal origin that are intended to be cooked before consumption, then the variability of the dose ingested is affected also by the cooking preferences. And here, by chance, I'm introducing this very famous equation. Forgive me, this is a Greek abbreviation for the food safety objective. It escaped my attention and I apologize for that. This is the FSO, the food safety objective, in a Greek abbreviation. But the equation for food safety objective is the H0 initial contamination plus the cumulative increases in log numbers minus the cumulative reductions wherever they happen, either in the processing or just during cooking before consumption. And all this should be less or equal to a food safety objective if available. If there is no food safety objective, then we don't need to apply this equation, but we simply can use the outcome of this dose distribution to convert it into probability of illness through a dose response model. So you see that the risk assessment is valid and applicable not only as a full risk assessment, where we end up in probability per serving, but is also valid if it stops a little bit earlier as a consumer exposure, because the consumer exposure is a really handful exercise in order to tell the industry and the authorities whether a food safety objective is met. But apparently the food safety objective is based on the final tolerable risk estimates, which is called appropriate level of protection. But this is the content of another lecture. So let's keep for now that when we are using a risk assessment approach, we can use a modular approach, okay, where the different modules represent the different compartments of the food supply chain, and we need to quantify the inputs that are used to explain or to estimate the increase or reduction in consumers' levels along the food supply chain, both deterministically or stochastically as probability distributions. And actually what I'm telling here is directly relevant to the growth predictor outputs, because the idea behind the QMRA module that I will present you is actually to translate this way of thinking into a software tool. This is the concept, to think food supply chain with a cumulative modular way. So this is the infogram, okay, that I showed you before, and this is practically the very first contact of the slides with the outputs of growth predictor QMRA module. So what I've done is I have split the food supply chain into 4 major compartments. One may argue why not more. This is not a problem. It can be done with 7, 8, 9, but I said that for simplicity, we can generalize the food supply chain description with up to 4 modules. And the starting point of risk assessment is the more critical. There are risk assessments from primary production to the consumptions. There are many risk assessments from retail to consumers, and there could be risk assessments that strongly limit to the domestic environment, or they go directly from retail to consumers without any further cooking. Okay, no matter what, as you will see, we can parameterize all the stages of the food supply chain and introduce all the variables that are affecting the pathogen behavior, either their growth or their inactivation, for every single food chain compartment. Then cumulatively, these calculations in the background are used to estimate the ingested dose. And then if you go further down, we will see in live demo, choosing the proper dose response model, we can convert this ingested dose into a probability of illness. And we can always introduce the amounts of servings to estimate from the probability of illness per serving the total cases per annum. Some things that I consider important to know about how to perform risk assessment in Growth Predictor. Growth Predictor offers some special features to be included in the risk assessment. First of all, for most of the compartments of the food supply, I offer the option of introducing the partitioning of the food. By partitioning, I mean that the food is not at this particular stage is subjected to slicing or cutting into smaller pieces. And this practically means that instead of having 100% of the initial food, you may have a 10% of that, so the dose is split into further fractions. This affects both, maybe not the concentration per gram, but certainly affects the prevalence. What affects also the prevalence and the concentration is the mixing process. Sometimes when we have the different pieces of food, they are mixed together in order to form a bigger piece of food. And in this case, depending on whether the mixed parts are both contaminated or one is uncontaminated, this might dilute or even increase the concentration and certainly affect the prevalence. And also, I use the option of cross-contamination. So this cross-contamination affects both the prevalence and the levels introduced at the stage where we define cross-contamination. So these are some extra features that somehow enrich our processes that better describe the handling that occurs during the food supply chain: partition, mixing, or cross-contamination. Now, the variability, the available probability distributions are a lot, as you will see. We have a list of different probability distributions that can be used for many different variables in the system. Could be on the initial contamination, the time, the temperature, the H0, which reflects the physiological state of the microorganism that is critical for growth, the cardinal values of the microorganisms, or even introduce the growth and the reduction directly as probability distributions. I also have included a probability distribution for serving size, plus the uncertainty in prevalence through a beta distribution. And finally, when it comes to the dose response, I offer a built-in dose response models based on published literature, but I thought of introducing some user-defined models in the sense, as those listed below, in the sense that I provide the equation in the code, and I ask the users through the tool to introduce the parameters into the equations that are included in the background. So the user does not need to know the equations. Of course, you can read the paper or the manual and get access to the equations. But if the user knows the expected dose response model, the tool offers the option to provide specific parameter values for these dose response models. And another critical aspect that I have introduced, which also requires a lot of computational capacity, but I found this very important, when we're introducing temperature distribution, we have three options to do that. When we're introducing temperature as an input value, I would say. First, we can always use a deterministic value, a fixed value, which means that we consider the average temperature in a step of the food supply chain simply because we don't have enough information about the variability of temperature. We may also introduce temperature as a probability distribution, selecting one of these four choices: normal, logistic, gamma, or PERT. But we may also introduce temperature as a cumulative set of dynamic profiles. So the tool offers a template to download to show the user how to append the different time temperature profiles one below the other, formulating an Excel file with multiple time temperature profiles. In this case, The output is also previewed. That's another thing to consider, that any option of probability distribution or fixed value is also graphically illustrated below the input box. So if you select a probability distribution, you see, depending on the parameters that you are asked to provide, what will be the shape of the input distribution. And similarly, when you are uploading a dynamic time temperature profile, or a set of dynamic time temperature profiles, you can see a preview of the different profiles you introduce. This way captures more realistically not the temperature as a variability distribution, but the temperature as multiple different dynamic profiles that may occur in the food supply chain. The final outputs are provided in tabular format or in graphical format. So the tabular format is here shown, and you will see it in a minute under live demonstration. So we have metrics associated with the dose, metrics associated with the illness. The selected tabular metrics is the average dose per serving, the mode, which is the most frequent value of the probability distribution of the ingested dose, and the 5, 50, and 95 percentile. So 50 apparently is the median percentile. And the same metrics are provided, the same percentiles are also available for the corresponding illness metrics, which are derived by using the proper dose response model that takes into account the estimated exposure dose by the consumers. Of course, apart from the tabular output, we also have the graphical output. So here is the histogram per serving, and this is the histogram of the final exposure. And then we have the translation of the exposure distribution into probability of illness. And here, as you can see, you may introduce also the prevalence, the distribution in the serving size, the number of iterations you want to apply, and as you will see, there is also a box for defining uncertainty in the prevalence by a beta distribution. Finally, once you perform, and for every time you are performing a risk assessment exercise with growth predictor, there is the tab where you can see the tabular and graphical illustrations of the risk, but there is also a tab that can be used to show you the results of sensitivity analysis. And the sensitivity analysis, this is illustrated by the tornado graph, and can be and the correlation coefficients that are used to do that are Spearman correlation and Pearson correlation. And you can see here that depending on the variables that are introduced in the sensitivity analysis, which practically means how sensitive your outputs are to the inputs, and the output could be probability of illness or exposure. So by sensitivity analysis, we see how sensitive is the exposure, the estimated exposure or the probability of illness estimated to the inputs, which is the cooking, for instance, the serving size, the initial level, and the change of the microorganism in the different compartments of the food supply chain. The change of the microorganism, the increase or reduction, apparently reflect the impact of time temperature conditions, as well as the product characteristics, which can be introduced stochastically or deterministically. So this is a very brief video of an older version. That's why you see less features here. But I thought that before I go on live demo, I can give a very brief video on how the risk assessment exercise should look like. So you see that there is a long column for each of the food supply chain compartments. And you may introduce the different variables like time, temperature, initial contamination via deterministic or stochastic values. Here I give you an example also of how you can introduce a dynamic time temperature profile for to account for the input of temperature. Apparently, if you are using a multiple let me pause the video. If you are using a multiple time temperature profile, then automatically the system understands that you are addressing both time and temperature. So you cannot use a time temperature profile and at the same time introduce a time variation, because it's one or the other. So once you have parameterized your food supply chain, including, as I will show you, also the product characteristics, which are further down, plus at the final stage of the domestic environment, the cooking practices, then you may introduce or not variation in the serving size, and then you are estimating the probability distribution of the ingested dose. Sorry, let's go back. I restart the video from the point where we stopped. In the meantime, I can tell you that you may use any of these four compartments as a starting point. You don't have to populate everything from the left to right, but you can use only the last two, for instance. By always clicking on render plots to resample, here you can introduce the variability in the serving size, and this will automatically update also the serving size and the exposure distribution. And then this is the probability of illness distribution, and below that you get the tabular format. By making differences in the input values, by changing the probability distribution of time, temperature, dose, prevalence, etc., or even by changing the growth characteristics, the product characteristics, then by clicking again, resample, then automatically the outcomes of risk assessment are updated within one or maybe a few seconds. And this is a cumulative process. Every time you are updating an input, either you have an automatic update of the final distributions, or you need to click render plot or resample. Then resamples the same distributions again and again. And the reason I thought of including this option here, the click to resample, is because depending on the complexity of the input variable, sometimes, and since we are talking about a web-based application, the number of iterations that can be run with all these input variables cannot be extremely high, cannot be 1 million. Of course, it can use 1 million, but it might take many hours. So in this case, it's recommended that you are making, for example, like 5 or 10,000 iterations, and then you can resample many times in order to increase the number of repeated samples. So this concludes the very first part, and I don't want to delay you more, so I will go through a kind of live demonstration for the next 5 minutes, as we did yesterday with the predictive modeling concepts, in order to be able to show you some features closer that cannot be captured easily by a video. Let me upload the software. So first of all, I remind you again, this is the link. You can refer to the yesterday presentation. Okay. And yesterday we saw all these different features, but here we will focus on modular process risk model. So we go here, the modular process risk model, and we see here a very preliminary output of this 4-compartment risk assessment. If you go, if you scroll down, remember that you have two independently scrolling windows. You have the last input window that scrolls differently from the right window. Huh? So you can always put the cursor on each of these windows and perform independent and not parallel screen scrollings. So here, for example, you have the initial contamination. You can use any type of probability distribution. You can use a normal distribution, or you can use a pair distribution, or you can even use an empirical discrete distribution. This is an interesting study. So you can, for example, say that you have different bins for the initial contamination level, okay, and you may have different probability for each of these bins. So summing up to 1, 3, okay, and then if you click import, then you automatically see preview the list of these discrete values. Even here, I can use a click to render plot, okay? I've done nothing more than simply changing the initial contamination level. But of course, this is not realistic, okay? So let's populate some other distributions. So I can populate the temperature distribution. I can give, for example, a pair distribution with a minimum, a mode, and the maximum value. And most important, I can also give a kind of distribution for the time conditions. Let's make it now 10 degrees, 10 days, for instance, plus minus 1. Okay. And then I have the option to use a growth model or a fixed value. Sometimes I don't have product characteristics, so I cannot really tell how the product and temperature may affect the growth, or I may not even have the growth model available. Of course, here we have the gamma models that I showed you before. So I can use, for example, growth model or a fixed value. If I use a fixed value, then I can directly introduce the